Good afternoon and welcome to the 13th Annual Scholarly Speaking Program. I'm Sarah Thomas and I'm the Director of the Hughey Library and Learning Center. I'm pleased and delighted to see you here today. Thank you so very much for coming. This program was initiated in 2005 to heighten the awareness of publications and presentations, to promote the library as a supporter of academic endeavors, and to educate the community to explore alternatives to scholarly communication, including open access. This program in bibliography is the result of the dedication of the Scholarly Speaking Committee members: David Ahrensberger, Chair; Linda Eisner; Joanne Evanoff; Kathy Hill; Laura Pope Robbins; Jessica Quarles; Susie Roth; and Patricia Watkins. Let's show our appreciation for their hard work to produce this program. Now, I'd like to introduce our Chancellor, Dr. Ayers, who will give the welcome. He is currently in Florida to attend the Board of Trustees meeting.
Good afternoon. Please accept my regrets for not being here today. As many of you know, I'm at the Board of Trustees, and the important thing I need to do to represent our campus. But having said that, you know where I'd rather be. Today's a wonderful day because we get to celebrate the scholarship, the applied research, and the research done by our faculty members here. And it's really just quite exceptional. Even more exceptional because almost all of it is done with undergraduate or graduate students. And that's that secret sauce that I think adds to our retention and our graduation rates, adds to your enjoyment of the job that you do. It's really a critical and important job that you do. And it just makes this such a special place, such a special community. I'm so pleased with the level of work that's being done. And I see that in especially the national recognition we get, but also the recognition by your disciplines of the excellence that each of you have. This is a very special faculty, and I would tell you that the high privilege of my life is to be a member of that faculty. To be a faculty member who's come up through the rank, who's done research and scholarship, and who continues to be interested in all those aspects of our craft. It's just such a very special privilege to be a part of all this. I'd also tell you it's very special because the Hughey Library sponsors this, and of course we're celebrating the 10th anniversary of the Hughey Library. And to Sarah and the whole gang there, thank you so much for what you do. So I look forward to hearing about all the great things that we talked about today. And when I get back, I'll try to get an update on all that. But have a great day today. Thank you for all you do on behalf of our campus, our university, and our students. And just have a great afternoon in the company of fellow scholars. God bless you all.
Thank you, Dr. Ayers. For our grand celebration this year, we have produced a bibliography with 49 authors. In January, when we made the call for publications and presentations, we received a variety of citations that covered a wide range of teaching, service, and research accomplishments. They included peer-reviewed publications and presentations, course materials, and student-generated research projects, interviews, and awards. The Scholarly Speaking Committee developed a criteria of inclusion to determine what citations would be included and what citations did not fit our definition of publications and presentations. Therefore, many of the citations you submitted might not have been included in the bibliography. Tomorrow, we will be distributing a survey to you to get your perspectives on this program. Please take your time to fill out the survey so that we can evaluate the effectiveness of the event and the bibliography and get your feedback to help us make changes. Please note that the program includes citations from the calendar year 2017 only from those authors who submitted them. This is not an official list. There may be other authors who are not included. This year, along with the certificate, you will receive a sugar cookie in the shape of an open access logo. This symbol of an open log is to encourage you to submit publications into the Embry-Riddle Scholarly Commons digital repository and to contribute to selected works so that your publications have a wider accessibility. The story of the creation of the open access cookie cutter is noted on the last page of the program. And this is the cookie cutter. Yes. This year, we are pleased to be able to provide a gift to you from the librarians. You may select a mug from the assortment of World Map, Constellation, Great Last Lines of Literature, How to Tie Knots, Pink, Freud, First Lines of Literature, Climate Change, Bat Signal Disappearing Mug, Wonder Woman Through the Years, and Crossword Puzzle. So think about what you would like. I'm excited to present those authors who have works published or papers presented in the year 2017. Now, I'd like to introduce Dr. Bloom, our Chief Academics Officer, who will congratulate you. When I call your name, please come up to the front to be recognized for your publications.
Okay, I am supposed to communicate a profound introduction to what we're about to do, but I won't. What's that?
Thank you, Dr. Bloom. Okay. Akan Almagavata. Mehran Andalibi. And did you know that Mehran, Evan Klein, and David Ahrensberger were instrumental in getting the open access cookie cutter manufactured at our rapid prototyping lab? Thank you, Mehran. Quentin Bailey, College of Arts and Sciences.
For the people who aren't showing up, we're going to be burning your publication.
That's on video, you know. It'll be on YouTube and for posterity. Okay, Catherine Benson. Dr. Bloom from College of Arts and Sciences, Department of Behavioral and Safety Science. Did you know, quote, he is not just someone who doesn't know what he is, but he is also someone who doesn't know what the meaning of what is, or is. Is this what he is, or what not?
Did you make that up?
Thank you, Dr. Bloom. Dr. Brent Bowen, David Ahrensberger, Department, Hazy Library and Learning Center. David Ahrensberger is not just a librarian, but also a marathon runner. Mesa, Phoenix, 2018 in February. Thomas Field. He said he was going to be here. Thomas Field. Security and Intelligence. Department, Intelligence, Studies, and Global Affairs. Please come forward and receive your certificate. Oh, people were supposed to be getting your cookies and your mug at this time. Oh, yes, okay. So, Dr. please get an open access cookie, sugar cookie, and your choice of a mug.
Wait, can I get mine too?
Yes, yes. So Dr. Bloom had a sneak preview, so he is choosing Pink Freud. Jonathan Gallimore. Oh, I saw him today. Jonathan is not only a professor, but he can hold his breath for 10 whole seconds. He can do the removable thumb trick better than anyone you have ever met. Jonathan Gallimore is not only a professor, but he is also an outdoor enthusiast that loves...
There he is. There he is.
Jonathan Gallimore is not only a professor, but he is also an outdoor enthusiast that loves camping and hiking. He is also a fisherman extraordinaire. He has seen, don't go away, over a dozen operas. He has 10 years of manufacturing experience with metal, wood, plastic. He built his first vehicle as a 1974 Chevy Blazer. He cannot see stereograms like the guy on Mallrats. Jonathan, you have, please select a cookie that is in the symbol of a open access. And then you have a selection of a mug over there, including Pink Floyd.
Woo!
That's one possibility. No, that's Dr. So you choose a cookie, select a cookie, and then select a mug. Oh, I'm so glad you.
I'm going for Pink Floyd. Heck yeah.
Okay, Michele Gazika. Is she here?
She had a psych club meeting. If you want, I can accept in her office.
I wouldn't trust her.
Okay, Javad Gorjadus. Oh, yes. College of Arts and Sciences and Department of Business. And select a cookie and select a mug. What are you going to select? How to tie knots, climate change. So many choices. Cindy Greenman from the College of Arts and Sciences, Department of Business. School of Business. Yes, we will change that. School of Business. And what are you selecting? Wonder Woman. Oh, there's Dr. Andali. Okay, Dr. Andali, College of Engineering, Mechanical Engineering. And I said this before, but Meharan Andalibi, Evan Klein, and David Ahrensberger were instrumental in getting the open access cookie cutter manufactured at our rapid prototyping lab. Select a cookie and select a mug. Oh, yes. That's open access, the symbol. Okay, Dawn Grove. And did you know Dawn got to race a cheetah named Eddie on foot in South Africa, and he won. John Haas, College of Intelligence, Security and Intelligence, Department Cyber Intelligence and Security. Did you know Aviation and Cybersecurity Opportunities for Applied Research has the 9th highest number of downloads in scholarly comments with 353 downloads, co-authored by Dr. Haas, cookie, and a mug. Timothy Holt, College of Aviation, Department of Applied Aviation Sciences, Dean. Did you know the Aircraft Cybersecurity and Information Exchange Safety Analysis for the Department of Commerce has the 6th highest number of downloads and scholarly comments with 700 downloads, co-authored by Timothy Holt. Please select a cookie and a mug. Oh, okay. Did I skip over? I went with green.
I think that was a Freudian slip.
Oh, my.
Pink
Okay,
Freudian
Aaron. So I had Aaron, then Nate, Chloe. College, Arts and Sciences, Department of Humanities and Communication. Did you know Nate is not just an English studies scholar, but he was also once a lead guitarist in a hardcore alternative band. Brennan Hughey, one of our guest speakers today, College of Arts and Sciences, Department Physics and Astronomy. Douglas Eisenberg. Dorothea Ivanova. College Aviation, Department of Applied Aviation Sciences.
Maybe you can give us a window, flip it to the camera.
And a cookie. Climate change. Curtis James. The College of Aviation, Department of Applied Aviation Sciences. Did you know that Curtis James is a native of Prescott and serves as a Scoutmaster for local BSA Troop 7014 in his spare time? And what is he going to choose? Well, yeah, open access, subliminal advertising. And you are, he's looking at several things, climate change, constellations, Wonder Woman, last lines, first line. Preston Jones. Eileen Landis Groom. College of Arts and Sciences, Department of Humanities and Communication. Did you know when Eileen first started working at Embry-Riddle, way before any development north of the campus, when deer and antelope roamed, and many coyotes and javelinas, she was sitting in the old cafeteria and looking at the floodplain area between the road to the pool and the road that used to be the main entrance road. Trotting along in a white fuzzy mass was a flock of sheep, about half the length of the library, along with the shepherd and his dogs. Did you know an ancestor on Eileen's father's side is one of the martyrs listed in the Mennonite Book of Martyrs?
He was a pighead.
So which mug are you going to choose? First lines, last lines?
Maybe that.
Maybe, okay. Bayou Lestari. Jackie Lukey. College of Aviation, Department of Applied Science, Aviation Sciences. Did you know trend analysis and operational performance indicators in the U.S. airline industry has the 7th highest number of downloads in scholarly comments, with 582 downloads co-authored by Jackie Lukey and Brent Bowen? Did you know a couple of years ago, Jackie jumped out of a perfectly good aircraft using a wingsuit for Tim Sestak's data gathering?
With a parachute.
What are you going to choose? Okay, Wonder Woman. Alan Malnar, College of Arts and Sciences, Department of Humanities and Communication.
Over there. I'm going to be on YouTube.
And then an open access cookie, sugar cookie, and then a mug. Kayla Martin. Did you know Kayla moonlights at JPL during the summer? Juan Mert. College Aviation Department, Aeronautical Science. Did you know designing case study research for pedagogical application and scholarly outcomes has the 19th highest number of downloads in scholarly commons with 175 downloads, co-authored by Jackie Lukey, Juan Merck, and Brent Bowen. Sarah Nelson, College of Aviation, Department Aeronautical Science. Did you know Sarah became a pilot because of a dare with a guy, and then 15 years later became a lawyer because of a bet with another guy, thus enjoying two great careers that are now combined at Riddle. Moral of the story, don't dare Sarah. What did you get? Wonder Woman. Okay. Michele Parker. Curtis Peacock. College, Arts and Sciences, Department, Humanities and Communication. Jenna Perry. Laura Pope Robbins. Ed Post, College Engineering, Department, Electrical, Computer, and Software Engineering. What are you going to do? Brian Ratchford. Rustin Reed, the College Arts and Sciences, Department, Behavioral and Safety Science. Did you know in 2016, Rustin was able to visit the bottom of an underground copper mine nearly 7,000 feet down where they were having trouble controlling heat stress. The rock surfaces, as well as the water pouring into the mine, were 180 degrees Fahrenheit. Joel Skipper. Timothy Sestak. College of Aviation, Department, Aeronautical Science. Brooke Shannon. Sam Seward. College Engineering, Department, Electrical, Computer, and Software Engineering. Mark Sinclair. College Aviation, Department of Applied Aviation Sciences. Did you know the extratropical transition of tropical cyclones, forecast challenges, current understanding, and future directions has the 17th highest number of downloads in scholarly commons with 239 downloads, co-authored by Mark Sinclair. Ahmed Ayanda Suleiman. College Engineering, Department, Electrical, Computer, and Software Engineering. Lance Trott. Jules Yemga. College Arts and Sciences, School of Business. Johnny Young. Michele Zanolin. College Arts and Sciences, Department, Physics and Astronomy. Did you know that 35 of Dr. Zanolin's articles can be found in scholarly commons, and he has a profile in selected works? Did you know that this month, the Scholarly Commons Digital Repository hit 1 million downloads since 2013? While the majority of the readers are from the United States, many are from the United Kingdom, India, France, China, Germany, and Canada, to name a few. And then Hong Jan. College Arts and Sciences, Department, Humanities and Communications. That's it for the certificates. Let's have a round of applause. Our recipients. Well, when I was growing up in Wyoming, my parents would take me out at the backyard at night, and we'd look up at the night sky, and they'd ask me, what's beyond the stars? What does it look like? What does it sound like? I was mesmerized from a very young age. I'm very grateful to them for giving me the gift of wonder. So here I am, so glad to be alive at this time to actually be able to hear what the universe sounds like. This year, we are honored to have 3 faculty from the College of Arts and Sciences as our guest speakers today. In 2017, the Nobel Prize in Physics was awarded to laureates from MIT and California Institute of Technology's architects of the LIGO project. Our very own Dr. Zanolin, Dr. Hughey, and Dr. Gretarsson are contributors to the LIGO project, the Laser Interferometer Gravitational Wave Observatory. With that, I introduce Dr. Zanolin, Dr. Hughey, Dr. Gretarsson, who will explain LIGO, listening to the sounds of space-time. If you come up.
All right, I'm going first. So we're going to tell you how LIGO works, what we can hear with it, and what the future holds. But I'm going to start off with trying to put this into a bigger context. And once I've done that, I'll explain how the detector works. I'll hand it off to Brennan, who will explain the current state of affairs and all about signals, and then Michele will explain the future. So LIGO, listening to the sounds of space-time. We like to think of LIGO as listening because we're already looking out there with telescopes. We've been doing that for a long time, and also with other types of telescopes, which I'm going to talk about shortly. But LIGO is very different. It really is like listening. It's like turning on the sound. We've been watching the symphony for a long time. There we go. So these are some pictures that are supposed to represent modern astronomy. Your typical sort of picture of astronomy is people looking through a telescope, maybe in a domed building, maybe with some assistance, and probably writing with a fountain pen in an onion leaf note. And that art is, of course, still something we use today, but has reached its apex, I suppose, in the Hubble telescope, which is up there on the top right. And traditional telescopes look at the universe and gather the information in visible light. So this is just normal light, and it's electromagnetic radiation at wavelengths that our eyes are receptive to. But those, of course, are not the only wavelengths that come to us. Nowadays, we try to capture all of the information coming to us from the universe, and the entire electromagnetic spectrum is of interest. And I can't put up detectors for the whole electromagnetic spectrum, so I've chosen detectors that look at approximately the top end and the bottom end. So we have gamma ray telescopes, the funny looking telescopes here on the below the Hubble Space Telescope. If I find my thing, I'll point to it. There it is. And they're mirrors. They kind of look like radio telescopes, but those are actually mirrors, and they are gathering blue light from Cherenkov radiation as high energy photons or particles hit the atmosphere. And that blue light is generated, as I say, by gamma rays or by other high energy particles called cosmic rays. So that's the high end of the electromagnetic spectrum. And here we have radio telescopes. We all know what a radio telescope looks like. Maybe you saw the movie Contact with Jodie Foster in it.
where she's listening for the aliens. Well, that was a radio telescope. And to be fair, they also have the analogy of listening because it's a single pixel aperture unless you have an array of them. And those are looking at the very longest wavelengths. Now, wavelengths sort of on a human scale, a meter or a few meters or so. And then down at the bottom here, we actually, I really should feel like Brennan should be explaining this because he worked on this for his PhD project. This is the Icecube Detector. And it also, the way I understand it, he's going to probably correct me, looks for Cherenkov radiation. All right, it's got the thumbs up, actually. And that is now from much more mysterious, much more ghostly particles called neutrinos, and the atmosphere is just not dense enough to have a high probability of interacting with them, or for them rather to bump into an air molecule. Rather, they need to go through something denser like ice or water, and there are something like 100 strings, is that about 100? Tell me, how many strings? 100?
Icecube's 89. So
89, I was pretty close. 89 strings of beads drilled down to about 3 kilometers down into the Antarctic ice sheet. And each bead has a photodetector on it. And so there are thousands of these beads hanging down there, and they can trace out the path of an incoming neutrino. And then finally, so that all of these messengers, so we like to call this multi-messenger astronomy, are listening or watching this astrophysical event. This is Eta Carinae, which is a binary star where the primary is about to go supernova, we think. And we gather all this information, and the final thing that we've been trying to gather for a while and have recently succeeded is to hear the undulations of space-time that have propagated from such events, such violent events, where there are large motions of mass distributions. And what you see here in this picture is this contraption. If I stand next to this, I'm about the same height as that thing. And so these mirrors are about yay big. And they are ultra pure glass. This lowest mirror here hangs from this upper piece of ultra pure glass, which hangs from a cascade of springs and ultimately hydraulic mechanisms to isolate it from the motion of the Earth. And the reason you need to isolate it and hang it like this is so that it doesn't move, or at least it doesn't move at the frequencies of interest. And so when a gravitational wave comes by, it does what gravity does, pulls on things. A gravitational wave is a stretch and a compression that then changes its sign as the gravitational wave propagates. So it'll be like, stretch, stretch, compression, stretch, compression, stretch, something along those lines. I don't have a slide for that, so I'm just going to act it. And it's going to pull on these mirrors and wiggle them at the frequencies of interest. These are audio frequencies, so you can in fact plug the output of our detectors that monitor the motion of these mirrors and hear the gravitational wave. So these are free. These are free moving. These are free to move. These are pendulums. These are just hanging there, and they can respond to the gravitational wave. And then the question is, well, okay, so you've got all these messengers. And we're going to concentrate particularly on LIGO here, and on my next slide after this I'll tell you the details of how LIGO works. But even within the spectrum of gravitational waves, now not even considering the electromagnetic spectrum or the spectrum of particles, there's a lot of information. And LIGO, down here on the right, lower right, That's an aerial photograph of LIGO. It's 4 kilometers in each direction, and that contraption hangs at the ends of each of these 2 tunnels, so actually 4 of those. And LIGO is a little bit like the gamma ray telescope. It's looking at the highest frequencies of gravitational wave disturbance. Looking at the highest signals. Those are things like pulsars, which are rapidly rotating collapsed stars, supernovae, exploding stars, and orbiting black holes, orbiting neutron stars that orbit and eventually spiral into their death and collapse into a larger neutron star and then a black hole or something along those lines. Slightly below those highest frequency waves, which are in the audio regime, so you could hear these, are gravitational waves from much heavier objects. Things like a large black hole eating a neutron star or another different compact object. You might also be able to hear, hopefully, certainly will be able to hear the initial stages of the in-spiral of 2 large black holes, and Brennan will talk about that. You would do that with a space version of LIGO. There has been a proposal out there for a long time called LISA, Laser Interferometer Space Antenna, which intends to basically send the test masses out into space and monitor the relative distance between them with lasers and have them be something like I can't remember the number, something like millions of kilometers apart, hundreds of thousands of kilometers, something like that. If you want to go lower frequency than that, you can't really detect them directly. But what you can do is you can listen for these very, very periodic signals coming from pulsars. Pulsars give rough radio signals at a very, very steady rate. Now, if those radio signals, as they propagate through space, are disturbed by a gravitational wave, it modulates that period, it modulates the frequency. And so you can discern the presence of a gravitational wave through the modulation of the period of a neutron star. This is a signal that's really only detectable for very long wavelength, very low frequency gravitational waves, such as you might get from the merger of 2 supermassive black holes of the type we have in the center of our galaxy. If you want to go even lower, you have to look at another indirect measure, the polarization changes on the background radiation in the early universe. That is a fossilized remnant, if you like, of the gravitational waves propagating throughout the early universe when it was much smaller. Okay, but my job was not to really give you just a big picture, but also to tell you how LIGO actually works. So I have one slide in about 1 minute. So let's concentrate on these here test masses. We call those hanging, the bottom mass on that hanging contraption, that pendulum, the test mass. That's where the mirror coating is on, that's why it looked a little golden. And that's the piece that matters. That's the thing that's going to get wiggled by the gravitational wave. There are 4 of them, as I mentioned, here, 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 here. They're arranged as you see there. And if you pay attention, these are quite far apart, 4 kilometers, 2.6 miles apart. And what these 2 perpendicular arms, we call these arms, are actually, okay, these guys are not allowed to yell at me for saying this, are optical flutes. A flute is a resonant column, a flute is a column of air that is made to resonate, right? This is a column of light that is made to resonate by trapping it between 2 mirrors. I have two columns here, orthogonal to one another, and that's because you want to be able to distinguish what a gravitational wave does from that of all other disturbances. So if a gravitational wave comes by and wiggles these mirrors, what happens is it spoils the resonance a little bit. And a little bit of that light that you're trapping between the mirrors spills out. So it's going to spill out. These are very highly reflective over here. These are a little bit less reflective. And what happens when you disturb these mirrors is the light spills out this way and back that way, back to this beam splitter. You've injected it from a laser, and there's all sorts of mechanisms here in the front that I can go into if you're interested. But ultimately, the light gets trapped in these arm cavities. And the reason they're orthogonal is because of what a gravitational wave does. And I'm going to have to, because I don't have a slide, I was on one lab 3, I'm going to act it out for you. Okay.
That was practice. It simultaneously stretches like that as it compresses space like that. And then as it travels, this one will get stretched and this one will be compressed. And stretch, compress. So yeah, get the picture?
Not yet, do it again.
Okay, so that's why it's in this pattern here, orthogonal orientation, because one of them is going to get squashed and the other one is going to get stretched as the gravitational wave comes down onto this detector. And what that does is it sends light out to this beam splitter from both of them. If they had both gotten compressed, the light would have gone back to the laser and re-injected with this power cycling over here, and nobody cares. But if one gets squashed and the other gets stretched, that forces the light through the magic of interference, which magic I won't go into. That forces it out of this side of the beam splitter. That light gets cleaned in the output mode cleaner and detected on these photodetectors down here. The amount of light on the photodetectors, solar cells, is proportional to the amount of stretch. Send it through an amplifier, record it on discs, send it through headphones, and you've got a voltage that depends on the amplitude of the gravitational wave. So it's a recording of the signal. And what you do with that signal after that is Brennan and Michele's primary concern.
Okay, thanks, Andri. Now that we've got a little bit of an overview about the technology, I want to talk a little bit about what we've done with it up to this point. So, gravitational waves, ripples in the fabric of space. Difficult to detect because space is very, very stiff. So if you're going to come up with something you could realistically detect in terms of the gravitational wave signature, you're going to want to do something like, I don't know, make up a couple of things that are going to rotate around each other, and it would help if those things were really, really massive, like greater than the mass of the sun, and it would help if they're rotating around each other very, very quickly. Well, it turns out there is something like that. In the universe, there are mergers of black holes together. Generally, they've been orbiting around each other for millions, if not billions of years, and eventually they're going to merge together into a single object. So this is the simulation that we're showing here. This is not a photo of it happening, but the idea is this is something similar to what an actual black hole merger would look like. So this is the signal that we've seen first in LIGO, the signature of two very massive black holes merging together. So this is a set of the observations of merging black holes that LIGO has observed so far. First one is here, and over the last couple years, since late 2015, we have a total of 6 black hole mergers that we've published in terms of the gravitational wave signature. So on this slide, you can see that being represented in a couple of different ways. There's the actual gravitational wave signature on amplitude versus time here. So you can see this, for example, on Sheldon's t-shirt in The Big Bang Theory in some episodes, for example, as well as other places. Shows up on keychains, etc. Another representation I'm partial to, because I helped make the figure in a couple of these cases, is frequency on this axis, time on this axis. So as the black holes get closer and closer together, they spin around more and more rapidly. The frequency of rotation increases until they merge together, giving you this sort of inverse Nike swoosh here that you see in these various figures. So this is the set of black hole detections that we've had from 2015 up until the end of our last observation run in August. Maybe a couple more that aren't published yet, but I shouldn't really talk about those. So this is one way of observing a gravitational wave signal, showing what we've seen in the gravitational wave strain from LIGO. But this is called listening to the sounds of space. So another thing you can do, which Andri alluded to, is actually put that gravitational wave signal through speakers and play the sound of a gravitational wave. So this is going to play through 4 times, twice at the actual frequency, twice more downsampled by a factor of 2 so you can hear it more clearly. And this is the first of our detections, which happened on September 14th, 2015, gravitational wave 150914. So if you can go ahead and play the movie. So it's a little subtle, but you hear that little water drop noise. That's basically the chirp of this thing that's shown here, the sort of whoop, as the black holes rotate around each other very, very rapidly, several times a second. And these black holes, mind you, are greater than the mass of the sun, so an incredibly energetic phenomenon. And you hear that little water droplet, which is literally the gravitational wave signal. We've literally listened to 2 black holes of greater than 30 times the mass of the sun each merge together 1.4 billion light years away. That was the water droplet you heard. So I think that's pretty cool. So with these black hole observations, we've actually contributed substantially in through our LIGO observations to the number of black holes whose mass we can measure. So this set of 6 observations here, you can see the constituent black holes that merged together and formed an even more massive black hole. And the general range here is that we're dealing with things several times the mass of the sun. So that gives you the scale of what we're talking about here. And one of the interesting things about what we've observed so far is it's kind of hard to make black holes this massive from the collapse of stars. These are really on the upper end of what we expect to see for black holes in the stellar mass range. So that's an interesting feature that publications are still teasing out from the observations we made of black holes up to this point. But we've done more than just observe, listen to gravitational waves from black holes. Towards the end of our last observing run, so this is again gravitational wave 170817, so it happened on August 8th, 2017, or August 17th, excuse me, 2017, we observed a different type of signal. So this sort of longer duration signal happening over seconds rather than milliseconds, if you work that backwards, look at what that signature is telling us, these 2 things that merged together only had a combined mass about 3 times the mass of the sun. Still pretty heavy, 3 times the mass of the sun is a lot, but compared to these black hole systems, this is a pretty light system merging together and making these ripples carrying away energy that we pick up with the LIGO detector. So based on these masses and a couple of pieces of corroborating evidence, we can pretty confidently say that in addition to black holes merging together, we have now listened to the merger of 2 neutron stars. So a neutron star is also going to result from the collapse of a massive star, but it hasn't quite got the mass and energetics of the collapse of a massive star into a black hole. So it's still a very, very compact object, just not the singularity of a black hole. So this is very much an artist's conception, don't panic, but this is basically a neutron star superimposed on Manhattan. Not a literal picture, it's not a Michael Bay movie, but this gives you the scale of it. So these neutron stars, still greater than the mass of the sun, typically around 1.4 times the solar mass, can be superimposed on about the scale of a city. Still pretty darn dense, but not as dense as a black hole. So this was picked up on August 17th, and this isn't the total story. Unlike black holes, in which we don't necessarily expect to observe a lot else, when these two neutron stars very rapidly rotate around each other and merge into a single object. So, basically what we expect to happen, since they're not these singularities like black holes, is they're going to rip each other apart, splaying out matter as part of the process. So as these two things tear each other apart, there's going to be an environment surrounding the collision. So that tells us there's going to be other signatures than gravitational waves. So that's the theoretical prediction, and it turns out that this is true in practice as well. So within less than 2 seconds of getting the gravitational wave signature, independently, telescopes out in space, Fermi as well as one or two others, picked up a burst of gamma rays. So gamma rays are these very, very high energy photons, and these gamma ray bursts show up about once per day that we can detect, and there was one within 2 seconds of this merger of a neutron star. That confirms a lot about what we expect to happen here. That confirms that most of these gamma ray bursts that happen over the duration of a couple seconds are probably coming from these neutron star mergers. So in addition to that, once this happened, we let everybody know that there was this crazy astrophysical event happening, and a number of our astrophysical astronomer partners followed up in other sort of wavelengths. So Andri talked about the electromagnetic spectrum. You've got all these instruments picking things up in the optical, in the X-ray, and the radio, and all of them were on high alert when we sent out the signal, hey, we've got gamma rays and a gravitational wave together. And there was a robust program of follow-up over the next days to weeks. So this is a figure out of a paper here, and each little line that you see here is a follow-up observation by one of these instruments. A little hard to see this in detail, but there's a massive list of optical telescopes, several radio telescopes, X-ray telescopes that all participated in this. So this is, as of August 2017, the first case of multi-messenger astronomy with gravitational waves. There's been some stuff with neutrinos before in supernova 1987A, but this is the first time we've been able to listen with gravitational waves and see the universe at the same time. So we've managed to pick up this signature in basically most of the range of the electromagnetic spectrum, in addition to gravitational waves. The only thing that's missing is the neutrinos, which neutrinos are close to my heart, so that kind of hurts. But we gotta save something for next time. So this is really not just a triumph of gravitational wave astronomy, this is a triumph of astronomy as a whole. Everybody got together, we can learn all kinds of things about the system based on all of these different messengers that we're looking at. So as a result of this, there is so much science that can be done. As I mentioned, this confirms the origin of short gamma ray bursts, which have been a little bit of a mystery since the 60s, confirms where gold and uranium are made in the universe, lets us do cosmology in new and exciting ways, lets us learn more about what's going on inside these neutron stars, and lets Quentin, my department chair, and other people look at some fundamental physics in terms of what's the speed of gravity, can we investigate Lorentz violation, and things like that. So that's a quick overview of what we've managed to do with LIGO in the last few years. But I want to emphasize that the field of gravitational wave astronomy, as true astronomy rather than a physics experiment, is less than 3 years old. From September 2015 to now, that's the entire extent of gravitational wave astronomy as an actual practical field. So there is so much more that we expect to be able to do with gravitational waves in the future, and here to tell you about some of that is Michele.
Thank you, guys. Okay, a lot of details. Let's see if I know. Oh, wait a second. Did I just turn it off?
The other talk, just give it a minute.
Oh, yeah, too.
Guys, bring up the other talk.
Laser. Okay, let's go back. No? Okay, so you just heard a lot of details, but I know if there is one message that you might want to take home is that space and time is not an empty container, but it's more like a gel. And it's a gel that can vibrate. And for the first time in history, 1,000 people were able to build an instrument that can record this vibration. So for 300 years since Galileo, we have been looking at the universe. Now we can listen to the universe. So this sound that Brennan just played is almost like the first noise of a baby, okay? I know it might not sound that interesting, but if you're thinking about the beginning of the life of a person, it means there will be a lot that will come. And so we've been looking at the symphony, and now we can listen to that. That's what is exciting, that is at the beginning of the new era of astronomy. The other thing I wanted to point out is that we're not just studying what happens in the universe now, but somehow we're studying the history of the universe, because this signal traveled for millions of years before coming to us. So these two black holes emerged, they emerged a long time ago. So obviously I'm very excited because this is good for our students and it's good for the excitement of the research. But I want to just emphasize these two things. And as I go and talk about the future, I wanted to stress a couple of things. The future is going to be two kind of things. It's going to be which kind of other sources we might try to listen to next, and how we can do that. And so one of the sources that we might listen to are supernovae, which are exploding stars. And I want to say why it ties in with the concept of history too. This drawing here, the Chinese characters, they come from a notebook of a Chinese astronomer in 1064. So about 1,000 years ago, there was this Chinese astronomer who was looking at a certain position in the sky. He said, oh look, looks like there is a star that was not there yesterday, and then it was there very bright for a few weeks, and then it disappeared. And then about 1,000 years after, we built a telescope that was pointing to the Crab Nebula, and we were able to observe the gas and the speed of the gas, and we said, well, when did this explosion start? And so, from the speed and the size, we were able to tell that explosion started about 1,000 years ago, in the position where the Chinese astronomers saw it. Okay? And about a couple of years ago, for the first time, humankind was able actually to calculate the dynamics of that explosion and the gravitational wave of that explosion. And now we want to build instruments that listen to that. This is a three-dimensional simulation. And obviously inside there is a lot of stuff happening. And for those of you that are scared about equation in physics, this is a slide you may like. Okay? So, general relativity, these are neutrino interactions, some approximation, hydrodynamics, there is all the fun stuff. And this stuff produces gravitational waves. Brennan shows an example of gravitational waves from binary system. This is an example of gravitational wave from supernovae. There is a little bit of a look at the turbulence. And so this is one of the next things we would like to listen. And if you're interested in knowing how they're supposed to sound, one of our freshmen put together a webpage that has about 1,400 different sounds of different explosion of supernovae calculated by supercomputers. These are extremely costly simulations. And they might not say much to an untrained ear, but they can help us both in designing the algorithm to detect them and also in instructing the physics. If you want to know how different it sounds, for example, from the binary system, maybe our friend there can play one. Can you play one? Well, it's hard to tell, right? But the way you have to look at this, think about this signal is that if you would play an ECG that measures your heart beating, it might not sound that interesting, but it's pretty full of information for your cardiologist, right? So we are cardiologists and we study the signal to get the information that is there. And so we have a network of detectors that is in operation, and Andri described some of the physics. And some are actually under construction, for example, this one in India. And there is a certain variety of features. There is this one, for example, that is in Japan. It's called Kagra. And it is built under a mountain where there is also the best neutrino detector in the world. And I actually think that it's fun for our students because we have a study road this summer where we're taking some students to go under the mountain and look at the details of the detector. But pretty much these are expensive machines, and yeah, LIGO costed about $1 billion, and now we have to design the next generation of instruments. And this is an example of the instrument we might design. So we have there's an international committee that where we're working on designing the instruments, and obviously there is a fight because everybody has their own favorite kind of source, and everybody wants the instrument tuned exactly for that source. But the main point is that it's a new era of astronomy, and I think we can offer a great service to our students, and most important is we have the joy of learning something new. Thank you.
Thank you. That was so fascinating. And as I said before, from a child in Wyoming to be able to see beyond the stars and to hear it, I am so thrilled and excited. Are there any questions for these scientists?
Thank you very much for this very educative lecture. I was listening to Professor Stephen Hawking from England some time ago, and he was saying that in another 200 years from now, he's kind of concerned that these planets might be hit by something that may kind of erase a good part of the human race. From your listening studies, can you confirm this, or it's just a kind of both? Thank you.
Okay, I'll start. I think the short answer is no, but we do know gamma ray bursts exist. We know they give up gravity waves, and there are some speculations that some of the early, maybe two of the early extinctions on Earth were due to a nearby gamma ray burst ionizing the atmosphere.
Yeah, I have a question more along the lines of the philosophy of science, okay? So I've heard that space-time is not a container, but it's a gel, okay? Are there implications for other kinds of scientific endeavors in physics, chemistry, biology, psychology, based on a different conception of space-time and how you measure things?
Well, we have a way to probe the details of the physics of space-time. And if we would be able, for example, to prove that wormholes are possible, like in the movie Interstellar, and it would change the way we perceive reality. And there are theories, for example, that perceive time as one of the variables as space, and so the past is just a different location, and some people perceive that all the events could exist at the same time. And so there are, at the end of the day, physicists are philosophers because they're trying to understand, how much they can capture from nature. So in terms of philosophical implication, I think there will be. In terms of practical application, we don't know yet, but we know, for example, that general relativity now is used for the GPS system, so technological application might come up. It is tricky because we don't have an estimate how much time it takes before they have an impact. When Faraday discovered the electromagnetic waves a couple of 100 years ago, I don't think he had in mind that there would be a cell phone today. So we don't know, but usually radical new things come from not radical new discovery, and this is a radically new discovery. So it's probably going to take a few decades before we can gauge what is the next wave of impact on the philosophy and the technological application. In terms of biology, I'm not sure, unless we travel through a wormhole. But I don't know.
What So just a quick follow-up. So if time is not a static entity, but some kind of dynamic phenomenon, are there implications for the fact that, like, subjectively people experience time as slow and fast? For example, in my classes, students perceive time as going very slow, so they want to leave. So is there an analogy between one and the other is my question.
Dr. Bloom, I doubt it. But I do think we may be on the cusp of a profound shift in our understanding of space-time and fundamental physics. There's a lot of stuff out there right now that we don't understand. We certainly understand some things about space and time. We've verified that they can wiggle and undulate and stretch. We know there's a lot out there that we completely don't understand. 70% of the universe is dark energy, another 20-something% dark matter. We don't know what either of those are, so we're pretty short on answers at the moment.
Other questions? Well, thank you so much, Pal.